All right, today we're going to focus on the second derivative and using analysis to find when a function f of x has a region that is concave up or concave down. All right, so we already talked about concave up meaning bowl up and concave down meaning bowl down pieces of the graph. But what I thought we could do is take a closer look and connect that with the idea of the second derivative. The second derivative is what's going to help us understand concavity, and here's why. All right, so let's say that these are sections of the graph of f of x, right? So this is a graph of f of x. And what I'm going to do is I'm going to put some points on here and just put a few points on here and then draw some tangents at those points. All right, so draw this tangent, and I can tell my tangents are slowly becoming more horizontal. Now, they're all negative on this section of the curve, which makes sense because my curve is decreasing, and that means f prime is negative. But something else is interesting about this curve. If I actually attach numbers here, so if I just estimate, so like this right here, let's say I say that's -2, and then this is a little bit more shallow. So maybe this is a slope of -1. Maybe this one's -1/2, and then this is almost 0. So I'll just call it 0. Notice those numbers that they are decreasing. Reverse, -2 to -1 to -1/2 to 0. Those are numbers that are increasing on a number line. I'm moving to the right on a number line. So if those are slope numbers, that means that the f prime graph, so all of these right here mean that f prime is increasing. The slope, f prime is the graph of the slopes. So the slopes are increasing, so f prime is increasing. If f prime is increasing, doesn't that mean that the derivative of this graph should be positive, right? We learned that if you take a derivative of a function, and the first derivative is a function, so if we take a derivative of that, then that should be positive if the function is increasing. So f double prime has to be greater than 0. And if I continue this trend, so if I take a point here and I draw my tangent, well, that looks like if I connected these up, they'd both be 0. And if I put a point here, draw a tangent, maybe 1/2, and then it gets a little, these are all positive, so we're getting a little more steeper, etc. Okay, so I can see that the numbers are trending more, increasing. So all of these numbers are increasing, so that means that my f prime, these are slope numbers, and f prime is the graph of all those slope numbers, then f prime is increasing. And therefore, that means the derivative of this graph must be positive. So f double prime is greater than 0. So everywhere where a function is concave up, you get the second derivative is positive. And so that's the idea behind the mean value theorem corollary that states that if a function is concave up, then the second derivative must be positive. Now you can certainly apply that idea to a concave down curve if I attach some slope numbers. So this looks like a pretty steep positive slope. So I'll say 2 there. Then it's getting a little bit more shallow. So maybe 1 and then 1/2 up here. What's happening with the numbers? And then if it gets up here to this flat section, I'm getting 0, 2, 1, 1/2. Those are decreasing, right? So these are slope numbers. These are the f prime numbers. If that means that f prime is decreasing. If a function's decreasing, then its derivative must be negative. So the derivative of that is f prime, so that must be negative. And so that takes us to the second part of the corollary, that if a function is concave down, then the second derivative must be negative. All right, and let me complete that. This should say f of x is concave down, not f double prime. So it's f of x is concave down when its second derivative is negative. All right, and then continue that. We could try more numbers over here, but you would see that trend, all these numbers would be decreasing slopes. All right. Now, we also talked about inflection points. That is where concavity changes, right? They are defined points. You can't have a point if it's not defined. So these are existing points on the graph of f of x where the function changes concavity. You either go from concave up to concave down or vice versa. All right. And it doesn't have to be a nice smooth curve. You can certainly have a curve like this, concave down and then concave up. So it can be pointy as well. All right. All right. So that's where the second derivative changes sign. That's what we're looking for. All right, so we need a strategy for figuring that out. And just like with the first derivative, when we were looking for where a function changes from increasing or decreasing, all we need to do is to figure out where the second derivative is equal to 0 or where the second derivative is undefined. And then we can evaluate around it to find where it's positive or negative. So that is the strategy that we're going to use. And we'll try some examples on the next video.